I want to go a little bit more in depth into some of the sensor performance metrics that will ultimately be of interest to you if you are picking a sensor for a project or sensor for some kind of application later down the line. We'll start with sensitivity, which is effectively the relationship between the output off an electrical signal from your sensor and the physical input. And this is often given as a ratio of the change in output to change in input. So it might be something like ohm per lux for the cadmium sulfide light or photoresistor that you have. Or for an accelerometer, you might have something like volts per meter per second squared. Volts for acceleration, or volts per G often is what it's given as, right? So you can have a number of these based on the type of sensor that you have. And another way to look at this is graphically. So if I look at sensor input on one axis and my sensor output on the y-axis here, I'm effectively defining my sensitivity, and I often write that as K. So I'm defining my sensitivity as the slope of that curve. And what you'll notice here is I've drawn this curve as nonlinear, and oftentimes a sensor will have a nonlinear response. And so I need to think of a sensitivity at a particular point. So at some input here, I'll define this as in 1. I might have a sensitivity that's basically defined by this slope right here. So this would be K at in 1. At a different, in this case, higher input, I'll have a different sensitivity. So in this case, you can see that sensitivity is much higher. That slope is much higher. So this would be my sensitivity at that input 2 equilibrium point. So as long as I'm, for example, I can assume a linear sensitivity if I'm staying within a particular range of an input. But if I'm trying to measure things over the entire range, I need to take into account that nonlinear sensitivity. And speaking of range, that will be the range of physical signals that can be converted to outputs by the sensor. And oftentimes you're talking about an input range. So Rin, the input range, might be defined as the maximum input signal that you can measure minus the minimum input signal that you can measure. You might often find this on a data sheet written as full-scale operating range, or FSO. And when you have particularly large ranges, we often define that range, instead of this just basic subtraction here, we define using decibels instead. So in this case, that range in decibels is going to be 20 log of the ratio of that maximum input to the minimum input, and that's in decibels once again. The accuracy of your sensor is going to be the largest expected error between the measured and the true signal. So that error in this case we define based on it's a statistical definition, some number of measured values minus the true value that I know something is at. So this might be kind of part of a calibration. On the data sheet, you might often see accuracy relative to that full-scale operating range. So for example, if you saw that the accuracy was defined as 1% FSO, and if you know from elsewhere on that data sheet, the full-scale operating range, say this is a temperature sensor, is 0 to 100 degrees C, then I would expect my accuracy, or that largest error, to be plus or minus 1 degree C. Right? Precision and accuracy are very often confused. Precision is a measure of a sensor's ability to give the same output over multiple measures of a given input. Or another way I could think of this is as reproducibility. Okay, the typical way to really distill accuracy versus precision is to show this kind of target example. So in this case, you have a group of samples, maybe from a sensor, measurements from a sensor that are all clustered together near the target, near the bullseye. So in this case, you would have a sensor, because they're near the bullseye, you have something that's accurate, and because they're clustered tightly together, you also have a sensor that's precise. Right, in this example right here, you have a bunch of measurements that are clustered together, but nowhere near the bullseye of the target. So in this case, you are definitely not accurate, but you are precise. And then in this final example, if I took kind of the mean of these measurements, they would be around that bullseye. So I do have an accurate sensor. But because they're so scattered around, right, the reproducibility of the measurement is not very good. So that means this sensor is not precise. And something that can often cause havoc in your measurement is noise. Noise is any part of your signal that's not due to the physical sensor signal that you're trying to sense, the measure end. So there's lots of different types of noise that you might encounter. So one example might be something that's fairly deterministic. So maybe the frequency of this is 60 hertz, right? So this would be a very deterministic noise signal that's superimposed on top of my measure end signal, which is the white line here. So the red signal is what I'd actually measure, so it's got the measure end signal plus my noise on top of it, and 60 hertz noise shows up everywhere. Right? But this is one type of noise that is deterministic. So I can kind of figure out what's going on with this noise, and I can potentially filter that out with something like a notch filter. Right? There are other types of noise that are a lot more random. And so in this case, maybe I have some kind of white noise that's superimposed on my signal. And so, one of the big questions is how I'm able to handle this kind of noise, especially if I'm trying to design sensors that are incredibly sensitive and can measure very, very small measure ends. So your resolution in a sensor is a little different than the resolution in ADC, which was defined by bits. This is a little bit more like that least significant bit that we had in the ADC. Resolution is going to be my minimum detectable change in the measure end. So that's going to be defined in units of the measure end. If I have I'm trying to measure a pressure, my resolution is going to be defined in pascals. If I'm trying to measure a current, my resolution is going to be defined in amps. So often if I have some kind of analog sensor and I have no input going into that sensor, so say it's an accelerometer and it's just sitting still, then I will have some level of noise that I'm measuring at my output. And this I'm typically calling the amplitude of the noise floor that I have from my sensor. And remember that this noise floor is going to be in my output units. So a very common definition for resolution is going to be that noise from your sensor divided by the sensitivity. And remember, sensitivity is giving me output over input. So if I have output units divided by output over input, I'll get my resolution in input units. So if I have an accelerometer, once again, I have output noise in volts. My sensitivity is in volts per G, like gravity. Then I'll get my resolution in G. Right? And a very common rule of thumb that you can use for these sensors as well is that the minimum detectable output will be approximately 3 times the noise floor. And so once again, I can think of this as basically adding a 3 in front of this if I want to go based on this rule of thumb. And finally, I want to talk a little bit about bandwidth. And bandwidth is going to be defined by the range of frequencies over which the sensor operates. So you may have seen a frequency plot like this before, where maybe you have kind of an amplitude of your sensor measured based on frequency. So if I have a sinusoidal input to my sensor, I'm looking at how that amplitude changes with the sinusoidal input. It kind of goes back to filters, but it's basic dynamics of the sensor. And so in this case, I can define a point at which I consider the amplitude still worth looking at, and that will ultimately define then my sensor bandwidth. Right? And the problem with this is I will still get some output even at these very high frequencies, but what this plot is telling me is that they might be too low for me to actually detect. And of course, I can have all sorts of other complications because I also get a phase shift as I start rolling off here too. Right, but these are a lot of interesting kind of performance metrics to look at when you're trying to decide on a sensor to use in a particular system, whether you're trying to measure something or trying to incorporate something into a control system.